Can folks in the chat hear me okay? Thanks. Okay, so as usual, don't forget the seating survey. Section 1, I do not have a pre-printed set of stuff here today because I've been trying to figure out the curve on the exams. So the upshots are that we have, we don't have content videos for this week. I will have them posted late so that you can use them for studying, for reviewing, but instead today and tomorrow I'm going to do live lectures on the content material for this week to help you with the Newton homeworks. So the only things that are due this week are the Newton homeworks on Friday. I will this week as well get an exam walkthrough video posted. The results of the exam, the scores were not up where I wanted them, and as there's a question here, what time is tomorrow's session? Tomorrow's session is noon. So the content that I'm going to lecture on today will be the same as the content that I will lecture on tomorrow. So I'm not expecting somebody who is in the Monday, Wednesday class to come to the Tuesday, Thursday class or vice versa. So I'm going to go over this week's material as if they were in content videos today. I'm going to do the same thing tomorrow. On the exam, the grades were not where I wanted them to be, and as a result of that, as I promised, I am going to implement some curves on the grades. I am still in the process of figuring out a curve that is reasonable, so I had hoped to have that done in time for now, but I do not quite have it done yet. So I will hopefully be able to get that figured out this afternoon. I've heard a number of people, say I failed the exam, this sort of thing. I want to reiterate that the exams do not have letter grades. What matters is accumulating points towards the final grade in the class. And even without the curve that I'm going to use, if I plug everybody's grades so far into the grade projection spreadsheet, the class is almost evenly divided between a projected end grade for the semester, about evenly divided between C's and B's. Now, that is not what I want, which is why I'm going to implement a curve. I would love to have, what I want to have is roughly equals C's, B's, and A's. And if people get higher than that, that is perfectly fine. But do not think of a low grade on the exams as failing. That is just not what it's going to be. That's not what it is. There's a question here, what was the average on the exam? It was, if I remember correctly, slightly lower than the first exam. So it was, I think, a 28 or a 29. The standard deviation is about the same as what it was on the first exam. I think the first exam it was about a 14, and this time I think it was about a 12. There were some scores that were up into the 60s on the exam, but like I said, I wanted them to be higher than that, and so I am going to implement some curves. The problem I'm facing in implementing the curves is that as I do it, I then look at the grade projection spreadsheets to see what that's going to end up being for the final grades, and if I do something to fix sort of the low end, it really screws up the high end and vice versa, and I don't want anybody to get screwed up over this. So I'm going to try to have that done, figured out this afternoon. Okay. I'm not planning in today's class to go over too much of the exam itself because I want to have the walkthrough video ready for you to be able to look at first rather than trying to handle it piecemeal. So my intent was to focus today on the content that is on this week's Newton homework, which is acids and bases. Are there any logistical questions anybody has before I get started on that? Okay, so acids and bases. The first place we need to start is with some definitions. And one of the problems with acids and bases is that we have three different sets of definitions. Question here, so we won't have content video quizzes. That's correct. We will not have content video quizzes this week. I will have the content videos themselves up, but they will be later and they'll cover the same material I'm going to be covering here. So you will have them to review the material, but it's not fair for me to post them and then give you like 2 days to get the quizzes done. Okay, we have three main definitions for acids and bases. The first one is the Arrhenius definition. And this is the first modern definition of acids and bases that was come up with. According to Arrhenius, an acid is a substance that when put in water dissociates to form H+ ions. And a base is the same thing, except that it forms OH- ions. Okay, so an example of an Arrhenius acid would be something like HCl, which we know is called hydrochloric acid. And the reaction this has when it goes into water is that it dissociates to form H+ aqueous and Cl- aqueous. An example of an Arrhenius base would be something like sodium hydroxide, which when we put it into water will form Na+, aqueous, and OH- aqueous. So this is the Arrhenius definition, and one of the advantages of this particular definition is that it is substance-based, meaning that you have a substance and you can identify it is an acid or it is a base. That's different from the other two definitions we're going to look at in a moment, but that's one sort of quality of the Arrhenius definition. The Arrhenius definition, unfortunately, has some downsides. So, for example, it is specific to water. And there are plenty of cases where something can act kind of like an acid or a base, but in some other solvent system, like ethanol or any number of situations. And so the Arrhenius definition is limited in that regard. It's also limited because while this hydroxide ion, for example, is the characteristic ion for something to be a base, there are things that you can put into water that will create hydroxide ions that do not do it by simple dissociation. So an example of that would be ammonia. We have NH3, which when it's dissolved in water is in equilibrium with, and so, excuse me, let me, H2O liquid. In water, what it does is it will form NH4+ aqueous and OH- aqueous. So ammonia, when you put it in water, creates this characteristic ion, the hydroxide ion, for a base, but it's not doing it by dissociating. And so we would like to be able to call this a base because you end up with something that is very similar to what you end up with if you take sodium hydroxide and dissolve it into water. but by the strict definition, it wouldn't be called a base. So that's why chemists don't tend to use the Arrhenius definition very much. It's important for historical purposes and to understand why we started calling things acids and bases, but in most senses, chemists have moved on. The second primary definition we have is the Bronsted-Lowry definition. These are two scientists who independently at about the same time came up with the same definitions. And for a Bronsted-Lowry acid or base, we are looking specifically at protons. So a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So several things to notice about these definitions. First, what do we mean by a proton here? Well, what we're talking about is the H+ ion. So we're not talking about a nuclear reaction where there's a proton that does something to change the nucleus of something else. We are talking about an exchange of an H+ ion, okay? The second thing to notice here is that we're talking about a process that is happening, not a substance. So an acid or a base in the Bronsted-Lowry definition is an acid or a base in the context of a reaction that is happening, not, you can't look at the Bronsted-Lowry definition and say this substance by itself is an acid or a base. It's part of a process. So let's take a look at this first example here. The HCl goes to H+ plus Cl minus, and see how that one works in the context of the Bronsted-Lowry definition. So if we have HCl aqueous goes to H+ aqueous and Cl minus aqueous, let's think about this thing right here. This, the H+ ion is just a simple proton. It is a hydrogen atom that has been stripped of its only electron. Or if it was originally in a bond, it's been stripped of all the bonding electrons. A proton is a very, very dense packet of positive charge. Its size is tiny compared to anything else. And so in the environment of water, that proton is going to associate itself with any electrons that it can find. And remember what water is. Water is H2O, and each oxygen has two lone pairs of electrons sticking off of it. And so there are lots of these electron pairs that are attached to the oxygens that are floating around on every molecule in the water. So what happens is that this proton associates itself with one of these lone pairs. And so in an aqueous solution, we don't really have H+ as an individual ion. What we have instead is the hydronium ion, which has an overall positive charge and has an extra hydrogen attached to it. So anytime we write this, H+ aqueous, it's not really H+ aqueous. It is really H3O+ aqueous, the hydronium ion. So we consider this to be a shorthand notation for this species right here. Now, even this is an approximation because this will actually associate with more water molecules to form, say, H5O2 plus, H7O3 plus, and so on. So all of these are approximations, but this one here is a much closer approximation to reality than the H plus ion by itself. Now, with that in mind, let's look at the process of HCl dissociating in water from the Bronsted-Lowry perspective. What we would want to write instead of what we have here is HCl aqueous plus H2O liquid goes to H3O plus aqueous plus Cl minus aqueous. So we need to understand that these two reactions as written here are representing exactly the same physical process. It's just that the second one here is better representing what's going on with the H plus ion. Okay. Now, if we think about what's happening in this reaction, the HCl is donating a proton, an H plus ion, to the water. So in this reaction, this is acting as a Bronsted-Lowry acid, and the water itself is acting as a Bronsted-Lowry base. Okay. So the Bronsted-Lowry definition is a definition that is happening in the context of a reaction. And in this particular reaction, the HCl is acting as an acid and the water is acting as a base. Now, let's take a look at this same kind of definition in light of this reaction up here, which we said that the Arrhenius definition does not call this a base, but we would like it to be a base because it makes the OH minus ion. Well, what's happening in this case? In this case, the water is donating a proton to the ammonia. So in this reaction, the water is a Bronsted-Lowry acid, and the ammonia is a Bronsted-Lowry base. So notice what we have going on here. In this reaction, water is acting as a base. In this reaction, water is acting as an acid. So water is a substance that has the ability to act in different reactions as either an acid or a base. Something that has that property is known as amphoteric. Can act as an acid and as a base in different reactions. So we do not define an acid or a base in terms of the substance in the Bronsted-Lowry model. We define it in terms of the reaction that is happening. Okay, so additionally, this kind of reaction this kind of definition of acids and bases can extend even beyond water. So, for example, if we have a case where we have CH3O minus in some kind of solution, and we add to that solution NH4 plus ions, then this could make CH3OH, which is methanol in solution, plus NH3 in solution. And so here we have the NH4 plus acting as an acid and the CH3O minus acting as a base by the Bronsted-Lowry definitions. And there's no water involved. And notice as well, there's no hydroxide involved, and there's no free H plus or hydronium ion involved. So the Bronsted-Lowry definition takes us beyond the confines of aqueous systems, and it takes us beyond the confines of hydroxide and hydronium. Now, there is a third definition that is attributed to Lewis, the same guy who came up with the idea of Lewis dot structures. And in his definition of acids and bases, it has to do with electron pairs. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So again, let us take a look at our example reaction, the HCl plus water. And this time I'm going to do it using Lewis structures. So here is our HCl, and here is our water molecule. Now, what I'm going to show you here is something that is called an arrow pushing mechanism. And the arrow pushing mechanism is a fundamental concept you'll go into in great detail in organic chemistry if you go on to that. We're not going to go into major detail with it, but it helps to illustrate this concept of Lewis acids and bases. So the idea of an arrow pushing mechanism is you draw an arrow showing how electrons move. So what we have going on here is that we have a pair of electrons here that are forming a bond to the hydrogen, and that is then pushing away the electrons here. And the reaction then produces our Cl minus ion there and our hydronium ion here. So this little bracket thing here, some people look at it and say that looks like a 7 minus. This is really supposed to be like the corner of a box around it, and it's saying that the whole thing here has a charge of -1, and this is saying this whole thing has a charge of a +1 on it. So notice how the arrows are moving here. The arrows are not showing where the nuclei go. The electrons are showing where the electrons go. So it's saying that this lone pair comes over and grabs the hydrogen, and this bonding pair of electrons goes over and goes onto the chlorine. So in this reaction that we've drawn, the water is donating a pair of electrons. So the water here is acting as a Lewis base. The hydrogen, as part of the hydrogen chloride here, is accepting that pair of electrons that's coming in. So this is the Lewis acid. And notice that this definition of which one's the acid and which one's the base matches what we got from Bronsted-Lowry. Exactly. The HCl is the acid, the water is the base in this reaction. The Lewis definitions here are, we are not going to be emphasizing them incredibly strongly here in this class, but they will become very important when you get onto organic chemistry and inorganic chemistry, because it can explain a lot of the electron movements that are used in these arrow pushing mechanisms once we get deeper into chemistry. We will mostly be focusing on the Bronsted-Lowry definition, but you should just be aware that the Lewis acid definition is also important and may be useful in some situations. Okay, that's it on the definitions for various kinds of acids and bases. Are there any questions anybody has on those definitions before we move on to some further topics? Okay, not seeing anything from the chat either. Okay, so the next thing to talk about is we're going to talk about water specifically because water is a primary solvent for the environment, for biology, and so on. And because these hydronium ions and hydroxide ions are relatively critical to understanding what's going on in water, it's a very it's a very common and important topic to deal with. So in water, we've already talked about the hydronium ion and the hydroxide ion. There's something water can do where water by itself can exchange a proton with the neighboring water. So you can make H3O plus and OH minus. This is known as the autodissociation of water. And I've written it here as an equilibrium. This equilibrium, the equilibrium constant for this has a specific label because it's so important, Kw for K of water. And at room temperature, so at around 25 degrees C, this equilibrium constant has a value of 10 to the minus 14 molar squared. I don't recommend memorizing very many things. Knowing this particular fact is so central to a lot of water behavior that this is one of the few things I do actually recommend memorizing or remembering. So remember as well how we write what the equilibrium constant expression looks like. We take the concentrations of the products over the concentrations of the reactants raised to their stoichiometric coefficients, but remember we exclude liquids and solids. So this is simply going to be the concentration of the hydronium ion times the concentration of the hydroxide ion. So in standard water, in water where nothing else has been added, we, because of the reaction stoichiometry here, we would have an equal amount of hydronium ion and hydroxide ion. Because if we start with none of this, and we imagine doing an ice table so that we are now forming this, we're going to have X and X, and so whatever is formed is going to be the same in both cases. Well, so how do we take 10 to the minus 14 and divide it up here if it's going to be the same? Well, that means that for neutral water, we have a concentration of hydronium ion that equals our concentration of hydroxide ion, which equals 10 to the minus 7th molar. Because 10 to the minus 7th molar times 10 to the minus 7th molar gives us 10 to the minus 14th molar. Okay. Now this equilibrium by Le Chatelier can be modified by adding other substances to the water. So if we added in some hydrochloric acid, which dissociates to form our hydronium ions here, let's think about what happens. It's going to happen is that this concentration is going to go up because of the HCl that was added. So with this equilibrium happening, which direction is equilibrium going to shift? Towards the reactants, right. So with it shifting towards the reactants, that means that the hydroxide ion concentration is going to go down. So if we add enough hydronium ion to make the H3O plus concentration go up to, say, 0.01 molar, so that's 10 to the minus 2 molar, right? What will our hydroxide ion concentration be? Because remember, we have this expression here. And from the chat, we have 10 to the minus 12. That's right, 10 to the minus 12 molar. So in water, at room temperature, our hydronium ion concentration times our hydroxide ion concentration will always be 10 to the minus 14. And so acids and bases, when we add an acid to water or add a base to water, it doesn't change what the product of the two is, but this equilibrium shifts so that the product equals 10 to the minus 14 molar. Now, it is a little bit inconvenient to be talking about various different orders of magnitude like this, 10 to the minus 14, 10 to the minus 2, 10 to the minus 12, all these sorts of things. So what chemists generally do is to use something called a P scale. So a P scale. P anything, like pH, POH, P anything, is equal to the negative log base 10 of that thing, or the concentration of that thing, okay? So pH is the negative log base 10 of the H plus ion concentration, which we understand to mean hydronium. POH would be the negative log base 10 of the hydroxide ion concentration. Now, let's think about what we mean when we say the negative log of it. Well, so if, in this case, we have log base 10 of 10 to the negative 2, that just gives us the negative 2. We have the negative of that, so here, the pH equals 2. Here, the log base 10 of 10 to the minus 12 is minus 12. So the POH in this case is 12. Okay. So notice here that what happens. We have the product of the concentrations always equals 10 to the minus 14, which means that the pH plus the POH always equals 14. So pH plus POH equals 14. And let's think about here neutral water. For neutral water, our pH and our POH equals 7. So when you have a pH of 7, you have an equal amount of hydroxide and hydronium. If you have a pH lower than 7, then that corresponds to a higher a higher hydronium ion concentration. So pH equals 7 is neutral. pH less than 7 is acidic because you have more hydronium than you do hydroxide. pH greater than 7 is basic because you have more hydroxide than you do hydronium. Okay. Any questions on the pH and the pOH scale or on the autodissociation of water and its equilibrium? Okay. Next thing to talk about is acid or base strength. Okay. So we tend to quantify, or we tend to describe a particular acid or base that we put into water as either being strong or weak. Now, a very common point of confusion would be trying to think of strong acid or strong base in terms of the pH, and that's the wrong direction to go. Don't think of it that way. What we mean by a strong acid is that if we take the acid and put it into water, then it will completely dissociate. Meaning that this is not an equilibrium, it dissociates completely and we only have the right-hand side. So however much HCl we put in, because HCl is a strong acid, it will completely dissociate into hydronium and chloride ions. Okay. A weak acid, so acetic acid is a good example of that. This is the acid that is in vinegar. CH3COOH, aqueous, plus H2O, liquid, has an equilibrium. So CH3COO minus aqueous, and I always seem to run off the side of the page, plus H3O plus aqueous. And so there's going to be some equilibrium constant for this reaction. Because this is so common, we call this a Ka, for A for acid, and it's going to have some value. We're going to have some equilibrium constant for the reaction. Any Ka is of the form HA plus H2O is in equilibrium with A minus plus H3O plus, liquid, aqueous, aqueous, aqueous. Okay, so we're going to have some kind of value for that. For a strong acid, the equilibrium constant is so high that the reverse reaction is effectively nothing. It effectively doesn't happen. So can you determine a complete dissociation strong acid because it is non-reversible? Yes. That's exactly what we're talking about. We're talking about a strong acid. It is non-reversible. So let me go back for a moment to what I said you need to avoid thinking about, just so that it's clear. It is very, very possible to have a dilute solution of a strong acid. So you don't put much HCl into your solution, and so your pH is going to be close to 7. Slightly below 7, only a little bit. and it's still a strong acid because it dissociates completely. You can also have a weak acid, like acetic acid, very, very concentrated, and so it is more acidic than this dilute solution of the strong acid we had. Weak and strong have nothing to do with how much hydronium ion you have, nothing at all. What it has to do with is, does the dissociation happen completely? That's all it is. So make very sure you keep that clear. Now, I'm actually going to look up really quickly the Ka for acetic acid. So 1.8 times 10 to the minus 5. 1.8 times 10 to the minus 5. And let's think about our units. Molarity times molarity over molarity. So it's going to be a single molar here. So let's see what we can do with this equilibrium. Let's do an ice table for it. So we have, I'm going to abbreviate the acetate ion as A here. Okay, and let's suppose we make about a 0.1 molar solution. So we'll start with 0.1 molar, 0, 0. Now this is going to be an interesting point here. I'm going to circle that in blue to come back to it. Okay. We want it to dissociate, so this is going to go down. This is going to go up, this is going to go up. X, X, 0.1 minus X. We have our Ka is 1.8 times 10 to the minus 5 molar equals X squared over 0.1 minus X. So we end up with 1.8 times 10 to the minus 6 minus 1.8 times 10 to the minus 5 times x equals x squared. So x squared equals minus 1.8 times 10 to the minus 5x. Not meaning that. X squared plus that minus 1.8 times 10 to the minus 6 equals 0. I'm going to pull up a quadratic formula calculator. Our coefficient for A is 1. Our coefficient for B is 1.8 times 10 to the negative 5. And our coefficient for C is negative 1.8 times 10 to the minus 6. And we find that X equals 0.00133 molar. Okay, so notice here that because this is a weak acid, and we have this particular equilibrium constant, that our concentration of the undissociated acid is going to be 0.1 minus 0.001, or 0.099, roughly. So Most of it is undissociated. And yet, we still have a measurable amount of the hydronium ion that we've formed. And so our pH is going to be negative log base 10 of 0.00133. I'm going to calculate that. Of 0.00133. And we get a pH, in this case, of 2.87. Now, very quickly, we can then determine the pOH, because remember, it's 14 minus that. So you're going to have a pOH of 11.13, which you could then use to go calculate the hydroxide ion concentration. Question from the chat. There will be no equilibrium constant for a strong acid. That's correct. Or the way you would put it is that the equilibrium constant is so large that you can completely neglect the presence of any residual HA. Now, I said I wanted to come back to this point right here, because remember we said that neutral water starts out with some hydronium ion in it already. The hydronium ion concentration initially is 10 to the minus 7th molar. Well, this right here, for the final hydronium ion concentration is huge compared to 10 to the minus 7. So calling this 0, which was an approximation, is nonetheless valid because it's negligible compared to the X that we ended up getting. So, so in this case, because we are dealing with a relatively concentrated acetic acid solution, we could ignore the amount of hydronium ion we started with. But that is always one thing you have to check after you do one of these calculations to see, was it in fact valid to ignore that extra amount? So there's a question in the chat, why is it log 0.0013 and not 0.099? So we are looking for pH, what we care about is this, not this. So here I was saying how much of it is undissociated. For the pH, I am looking at the negative log of the concentration of the hydronium ion, which is just X. Okay. So, so this is the concept of weak acid equilibria. You can do exactly the same thing with weak bases. So we already talked about the example of NH3 plus H2O in equilibrium with NH4 plus OH minus. This one is also a weak substance, a weak, in this case, base. So we would have, in this case, a KB instead of a Ka. But it's of exactly the same form. So it's going to be concentration of NH4 plus, concentration OH minus, over concentration of the undissociated, or the unreacted portion NH3. And so the calculation would be exactly the same kind of thing. It's just you're looking at hydroxide instead of hydronium that's getting formed. Okay. There is a few other, actually before I go on, are there any questions about strong versus weak acids and the idea of the equilibrium constants for those? Okay, so very often you will see the p-scale that we talked about earlier, the negative log of whatever it is, used for Kas and Kbs as well. So if we have our Ka for acetic acid, 1.8 times 10 to the minus 5 molar, well, it can be somewhat inconvenient sometimes to try to keep track of the the exponents and the scientific notation. So we can instead have the pKa, which is just going to be the negative log base 10 of the Ka. And so plugging that into a calculator, negative log base 10 of 1.8 times 10 to the negative 5th gives us 4.74. And so we can represent this same information as a pKa rather than as a Ka. So that way, you're not dealing with scientific notation. You're just dealing with having a decimal number. And so the higher the pKa, the smaller the Ka. Now, just to make it very clear, sometimes if you have the pKa and you need to find the Ka so that you can do the ice table calculation, the inverse of this process is Ka equals 10 to the negative pKa. So this is simply the inverse function of what we have here. And the same is true for hydronium ion concentration in pH and the hydroxide ion concentration in POH. Okay. Let's look at one more detail of this particular reaction. Okay. So remember that we wrote this here as though we are going from left to right. Well, we also have to remember that there is a right to left that's going on at the same time. So this is the Bronsted-Lowry acid. This is the Bronsted-Lowry base in this reaction. But in the reverse reaction, notice that the hydronium ion here is donating a proton to the acetate ion. So if this is donating a proton, this for the reverse reaction is an acid, and this for the reverse reaction is a base. Now, they're related to each other. So we call these the conjugate base and the conjugate acid. So the acid on one side and the conjugate base on the other side act as a pair. The acid is the thing that gives up the proton going the other way, and the conjugate base of that acid is what it looks like after it's lost its proton. The base is the thing that is accepting the proton going in the reaction going the forward direction, and the base's conjugate acid is what it looks like after it has accepted that proton. Now let's take that one step further and write the reaction going the other direction. So we have A minus aqueous plus H3O plus aqueous goes to HA aqueous plus H2O liquid. Now remember our autodissociation of water. So I'm going to write 2H2O liquid is in equilibrium with H3O plus aqueous plus OH minus aqueous. Because both of these things are going on simultaneously, right? They're both equilibria, both happening. Let's add these two lines together and see what we get. Well, we get A minus plus H3O plus 2H2O is in equilibrium with HA plus H2O plus H3O plus. I'm off the bottom, aren't I? Okay, let's bring that back up. Plus OH minus. Okay, let's cancel out the stuff that's on both sides. So the H3O pluses cancel out. One of the H2Os cancels. And so we end up with A minus aqueous plus a single H2O liquid is in equilibrium with HA aqueous plus OH minus aqueous. Notice what we now have here. We have this, the A minus aqueous ion, pulling a proton off of the water. So in this reaction, this is acting as the acid. This is acting as the base. And we can, of course, come over here and say this is the conjugate acid. And this is the conjugate base. But what we have is that we have the acetate ion that we've added going into water, and it forms hydroxide. So if we decided to make a solution of, say, sodium acetate, it will be a basic solution. So this CH3COO minus ion, that is part of this, this salt. The acetate ion, remember, is the conjugate base of acetic acid. And so if we make a solution of the salt of the conjugate base, we just showed that what we get is a basic solution because we now have a hydroxide ion concentration that has gone up. Any questions on that concept? Okay, so the question then becomes, can we find, for this reaction of the salt, what is its Kb? Well, it turns out that we can relate the Kb to the Ka for acetic acid in a relatively straightforward way. So the relation to remember is that for a conjugate acid-base pair is that the Ka times the Kb equals Kw. In the, when I put the content video together that goes over this particular detail, I will go through the derivation of that so you see where it comes from. but for the purposes of the Newton homework and such, this is this is what you need to what you might need to know. So so in our case of acetic acid, so yeah, so CH3COOH has a Ka of 1.8 times 10 to the minus 5 molar. Then the CH3COO minus ion has a Kb of Kw divided by Ka. So again, I need to type that in. So 1.8 times, I'm sorry, 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And we get 5.6 times 10 to the negative 10 molar. Similarly, if you are more comfortable talking about the pKa and the pKb, pKa plus pKb equals 14. Okay. We are approaching being out of time. Does anybody have any wrap-up questions on acid-base content for this week? So all of what was talked about is going to be covered again in the content videos. Yes, it will be. And like I said, there's the only extra information that I'm anticipating being in the content videos will be the derivation of this relationship here, the Ka times Kb equals Kw. And I don't know that you need to know that because it's, I don't know that you need to know that because it's a, I'm not going to be asking you to rederive that. Should the Kb be to times 10 to the negative 9? I don't think so. I think if you take these two numbers and multiply them together, I think you get 10 to the negative 14. I will double check that. If I can get my calculator up here. So 1.8 times 10 to the negative 5 times 5.6 times 10 to the negative 10. And the base 10 log. Yep, and that's, yeah, so that, and that ends up with being 10 to the negative 14. Are we going over different content Wednesday? So Wednesday, I'm not going to be moving on from this content, but I'm going to be going over Muddy's points and stuff like that, questions that come up about the material based on what you guys end up getting confused about as you're trying to do the homework. So I'll be addressing questions and concerns at that point. So what I have gone through so far here is, I believe, the full set of material that I had intended to cover in the content videos for this week. All right, let's call it for today. Thank you very much.